All right. As we continue our exploration into these different physical characteristics of rational functions, we do have the existence of horizontal asymptotes. And horizontal asymptotes have some similarities to vertical asymptotes, but also one really major difference, which I think we'll talk about in person. What I'm going to do here is I'm just going to leave. Well, what you should do right now is you should pause this video and put this down in your notes. Okay. So I'm going to say hit pause. Okay. Hopefully you paused and you wrote this down. Let's talk about what it all means. Yeah. So when you have a rational function, a lot of you have to have some degree of x in the denominator. Okay. You don't have to have a degree of x in the numerator. Like just as an example, when we have this, right? This is a rational function, right? It's x to the first. If we wanted to get super weird with it, we could say that this is 1x to the 0 over x to the first, right? Because anything to the 0 power is 1. So again, this simplifies to be 1 over x. So technically speaking, even if we don't have x in the numerator, we could call it x to the 0. But a lot of these rational functions do have another x term in the numerator as well. Now, we're not really concerned with anything else that comes after this. So I know I wrote C and I wrote D, but that's immaterial. Okay. What we're really concerned with is two values. The values of the degree in the numerator and denominator, and the values of the leading coefficients. Okay. And the test for horizontal asymptotes deals with these degrees, and what we're calling M and N. So we would say if m is less than n, so if the degree of the numerator is less than the degree of the denominator, the horizontal asymptote is automatically y equals 0. No questions asked. In terms of why that is, I want to have that discussion with you guys, but I think it would be better explained in person. Okay. So for right now, just take my word for it on this, and then we'll talk about the interesting characteristics of horizontal asymptotes when we meet in person. Okay. If the degrees are the same, the horizontal asymptote is the line y equals, and it's the ratio of a over b. Okay. And a is the leading coefficient on the top, b is the leading coefficient on the bottom. If you have a degree on the top that is greater than the degree on the bottom, there is no horizontal asymptote. Okay. However, there is one very specific case where the degree of the numerator is exactly one more than the degree of the denominator. So just as an example, if you had a function and on top you had 3x cubed, blah, 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 and on the bottom you had 2x squared, blah, 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 blah. This degree of 3 is exactly 1 unit larger than this. When that happens, we get a slant asymptote. And that slant asymptote looks like one of these slope-intercept form lines. And we find it by using long division of polynomials. So just when you thought you weren't going to have to do this because synthetic division is better and easier, we still need to use long division in some instances. Okay, and we'll talk about that again in a future video. So if we look at the problem that we've been looking at this entire time, right, and we're looking for the horizontal asymptote to this graph. Now, if you've watched the previous videos, and we've always talked like, well, you want to make sure that you factor this whole thing out, right? Because you're going to want to know what the zeros are up top, and you're going to want to know what the zeros are on the bottom for the x-intercepts, right? The zeros up here are the x-intercepts, and the zeros down here get excluded from the domain, and so on and so forth. Finding the horizontal asymptote is easier with the original form of the function because we want to know what's the degree on the top. It's a 2. What's the degree on the bottom? Also a 2. So we've reached this status for our horizontal asymptote. So the horizontal asymptote is the ratio of a to b. Well, a is 2, the leading coefficient here. B is 1. Therefore, we have a horizontal asymptote of y equals 2 over 1, which is y equals 2, right? And remember that any line that starts as y equals and it's just some number, that's a horizontal line. That's why it's a horizontal asymptote. That's why our vertical asymptotes are x equals some number, right? So we saw that in a previous video. So here, if we look at this graph and we zoom out, and we did a little work with this when we were talking about the range, we kind of saw this happening. As we approach positive infinity on the x-axis, the y-coordinates 2.141, 2.140, 2.139, right? Very slowly getting closer and closer to 2 as the x values go all the way out to infinity. As we approach negative infinity, moving all the way to the left, our y values slowly grow towards 2, right? And if we throw in the line y equals 2 here, we can see again as we come all the way out here. Better yet, let's zoom all the way out. Okay, we're at negative 240 and the y coordinate is 1.988, right? And we could do this dance all night. We could keep going. Look at how slowly that y coordinate is going up. We're at negative 1,758 and the y coordinate is still 1.998, right? We come out here to 3,000, 2.001. So just dancing on top of 2. And then all the way over here, just underneath that value of 2. So that's where we can see that horizontal asymptote as we move out towards the infinities, right? But we can tell what it is just by looking at the form of the function. And we're going to talk about how this works. Like I said, in person, it's a much better discussion to have that way. Okay, but make sure you have these tests in your notes and make sure that when you're finding the horizontal asymptote, the factored form isn't necessarily going to help you as much as the original form of the function.